can go through all 10 questions of our quiz 1. Yeah. I will do in 3 parts. Part 1, 2, 3. For the first 2 parts, each one 3 questions. Part 3, 4 questions. Yeah. So we can cover all 10 questions. All right, so let's start. B.3, explanation of quiz 1 questions, part 1. Yeah. The first question, yeah. Oh, before I start the explanation, so let me give you some general explanation about the questions I make for all 6 quizzes for this class. Yeah. Some students send me email telling me the answers of some of the questions cannot be found, or so those students just said the original sentences like some of the questions I didn't cover in lecture notes. Yeah. Because as I remember, 2 students said things like that. Yeah. But actually, I want to let you know all the materials I put in my quizzes, all covered in the lectures. Yeah. Why still a small number of students, so they feel not covered? The question is, I think the answer is like this. I never give straightforward questions. So this is when I design questions. So I never give straightforward question. All right. What do you mean straightforward questions? That means the answer can be found easily in the notes or textbooks. I don't like to give those questions because in that way, you do not need to understand anything. You just look at your notes or look at your textbook, do some search. So if you can find a way to do the search, keywords-based search, you can find the answer. That's not a good way of learning. So I try to discourage that behavior. Yeah, because in that way, you do not need to understand anything, right? Just try to match by words. So that's not a good way. Excuse me. Oh, all right. I want to encourage you really use your thinking to solve these problems. Thinking is the most important thing for this class. So some of the questions, when I designed them, I tried to make it a little tricky. Yeah. You have to apply some special techniques to find the answer. So you will see in my explanation, you will see those questions, there is, some relatively deep understanding behind it. Otherwise, it looks like not very useful. Okay, all these quiz questions, if you do not need to pay a lot of effort, it is not very useful. All right, yeah. So because each semester I got similar questions like this. So at the beginning, I want to explain a little bit. All right, so let's start. Question number 1. To evaluate a polynomial, the higher the degree it has, the more multiplications we need. Here we talk about the general rule. Here I do not say anything. Here I do not put any special condition, right? So here we are talking about the general rule. Is this true in general? Yeah, because one student sent me a question asking about, special situation or the general like that. So it's a general case. In other words, if you can find a counterexample, it is false. One counterexample can disprove it. That's simple. All right? Yeah, here. Yeah. The higher the degree it has, the more multiplications we need. So think about that. The higher the degree, can you find a polynomial with lower degree, but that requires more multiplication than some polynomial with higher degree, but fewer multiplication? Can you get that counterexample? Yes, we can. All right, so here, let me put a, relatively simple example. So let me create a polynomial with a0 plus a1x plus a2x squared plus a3x cubed. Cubic polynomial. In this case, how many multiplications do you need to find its value? In general, here, all these coefficients given in an arbitrary way. Yeah. So you cannot expect any special pattern there. No special pattern there. Yeah. In that situation, by Horner's rule, all right, so the answer is 3, right? The same as that degree number, the multiplication, 3. Okay, yeah. So this is our first half of the counterexample. The second half, all right, yeah. Let me use P1, okay? The second P2 of x to the 4th. Only one term, x to the 4th. It's a special one. It's a special one, all right? But here you can see, but here you can see the degree number 4 greater than 3, right? Yeah. So that means the higher the degree it has, if based on this statement, the higher degree it should have more multiplications, right? Yeah. But here we know we can calculate with 2 x squared times x squared, right? But the x squared, we need 1 multiplication, right? So 1 here, 1 here. Total 2. 2 and 3, 2 less than 3, right? Yeah. So this is the counterexample. After we find a counterexample, it's false. How about that? Okay. All right. That's the first question. Second question. When we solve some counting problems, sometimes it is a good idea to work on a few cases with small data sizes first. Then we can extend our solutions to the general case. If this strategy here, actually I described one simple strategy. If this strategy is good or not, or if it is useful in our problem solving for computing problems. In my lectures, if you watch the videos in my lectures, I mentioned this strategy many times, several times. Yeah, we use this strategy frequently. Yeah. So definitely, it's correct, true. Now, here, let me explain a little more why it is an effective strategy. So let me explain that. Why it is an effective strategy. Yeah. The thing is, when we work on a computing problem, we want to get some experience, right? Yeah. Sometimes we don't have any experience. Yeah. So we want to understand this problem better so that we can get insight of the problem. Okay, so one thing we need, understanding of the problem. But how do you get some understanding? How do you get chance? How do you get experience working on this problem? And you can make some progress, especially you can make some progress. Yeah, the simple way, work on some simple cases. All right, yeah. After that, you have some experience, right? All right. With that experience, yeah, now you have some experience. You can find rules. From that experience, can you find some rules? We try to find some common rules, right? If you can get some common rules, or sometimes we call insight. Can you observe some insight? After that, then we can solve the general case. How about that? So that strategy is very effective. It is very effective. Okay. All right. Our last question of this video, question number 3. Is the execution time of a program a stable measure for the efficiency of the algorithm, right? Yeah. Answer is no. Answer is no. Why is that? In my lectures, I explained, the whole thing. Yeah. The reason, I explained that. The reason is the execution time rely on machines, right? Rely on machines. Yeah. Some people can use very powerful machines. Some people, use some very slow, very old machines. It's possible, right? Yeah. Yeah. Because we just want to learn algorithms, right? Yeah. We just need a machine that works, right? We do not require, extremely powerful machine. Yeah. So in that situation, execution time on different machines could be very different. So we do not rely on that kind of difference. Okay. All right. Another thing, remember I also mentioned another factor, programming skills, right? Yeah. Some programmers with a lot of experience, they have, some very smart ways to write their programs. So that could also make difference, right? So they can make the program runs faster. Yeah. They can that's another factor that can change the execution time. All right. So in that case, we say it's now stable. Now stable. Yeah. Then we try to find a more stable measure. All right. Yeah. So what is the more stable measure? Okay. So we count the number of basic operations. All right? Count the number of basic operations. So this number more stable. All right? More stable than that execution time. All right, so that's our B.3 video.